Alrighty, our 10 kilogram block is initially at rest. To calculate the work done, so we're going to do A, our work is equal to our force times by our displacement. So we are applying a 100 Newton force, but it's at 60 degrees above the horizontal. So we have our block that is being pulled at 60 degrees here. So therefore, it's moving in that direction, so therefore only the component along that direction is going to be applying the work. So our work in this situation is going to be our F cos of 60 times by the displacement. So that is going to be our 100 times by cos 60 times by our displacement, which is 5 meters, which should get us the value of 250 joules. As the object is only moving in the horizontal direction, for B, our change in potential energy is going to be equal to 0. That means that the work done is going to be equal to our change in kinetic energy, so therefore our change in kinetic energy is going to be equal to our work done, so it's going to be equal to 250 joules. You can certainly go ahead and find the final velocity of it, knowing that it initially starts at rest, but the fact is that this way of actually equating energies can be quite useful. C, we know that the change in kinetic energy is going to be equal to 250 joules. We know that it initially starts at rest, so that means that our change in kinetic energy is going to be equal to 250 joules, which is then going to be equal to our half mv squared. So that means that our final velocity, our v, is going to be equal to the square root of 2 times our change in kinetic energy, which is going to be our 250, divided by our mass, and our mass is going to be 10 kilograms, which should come out as being approximately the 7.07 meters per second. Now the question regarding friction. So in this situation, our block, which is being pulled across, has still got that 100 newtons along here. It's going to be looking at the component that's moving this way, which we know is going to do an amount of work of 250 joules. But we also are going to have a frictional force doing work, but its force is going to be in the opposite direction. It's doing 20 newtons worth of force there, but its displacement is still going to be along this direction here. Its displacement is still parallel to the motion of it, so it's still going to be traveling the 5 meters. That means for D, the sum of the work being done, which is going to be giving us the change in the kinetic energy in this situation, is going to be the force parallel times the displacement, and that's due to our string, plus our force due to friction times by our displacement. The only problem is that the force of friction is applying in the opposite direction. So let's change that from a positive to a negative. So we are going to have our 100 cos 60 degrees times by our displacement of 5 minus our 20 newtons of frictional force times by a displacement of 5. So this should get us our 250 joules minus, 20 times 5, 100 joules. So therefore, our net work done on the system is then going to be 150 joules. Therefore, our change in velocity is going to be using the same formula as above. So our change in kinetic energy is going to be equal to our half mv squared. Our v is then going to be equal to the square root of 2 times the change in the kinetic energy divided by the mass, which is then going to be equal to the square root of 2 times the 150 joules divided by 10, which should come out as being 5.48 meters per second.